Hoş geldiniz. Okay, welcome everybody. I'm Ali Alpar, the president of Bilim Akademisi, the Science Academy. We are being very informal today. We do not have somebody to introduce everybody else. So I will first invite our host, the president of Bilgi University, Profesör Yazgan, to start the proceedings. Professor Yazgan.
Okay, thank you very much, Professor Alpar. I'll also be. I would like to be a little bit informal, but I'm gonna. I have a semi-formal speech here that I would like to share with you. So let me start with my speech, and then I will leave the floor to the participants of this event. So first of all, let me welcome you all to the Innovation and Science Conference organized by the Science Academy. As Istanbul Bilgi University, we feel very privileged and proud to host this traditional event in our main campus, Central Istanbul. We are privileged also to have Professor Günter Stock among us, who will be our key speaker for the conference. Let me give a warm welcome to our main guest, who also chairs the Einstein Foundation in Berlin. The conference will focus on innovation and basic research, putting the emphasis on the biotech industry, which is not at all my field of expertise. So I will gladly leave the floor to the experts to discuss about this matter. I would, however, like to underline some salient aspects of today's challenges regarding innovation and basic research. We have unfortunately entered into a dark era where many different forms of rejection and denial of scientific methods and findings appear, unfortunately, in various countries and societies all over the world. Even in the most developed and wealthy countries, administrations rejecting modernism, rationalism, and international cooperation come to power. In such a hazardous transitional period, scientific research, cooperation, and innovation acquire even greater importance. On the other hand, very sophisticated research work is being carried out more and more globally through scientific networks of corporations. More and more, the interpenetration of economies has created converging needs. More and more globalization produced similar challenges. Obviously, there are many different definitions of what basic research is. It should also be added that there are numerous definitions of innovation, counting at least in the hundreds. Current debates in the academia emphasize that innovations are not only new products and technological production processes, but refer to many more and wider phenomena, including new organizational forms and creation of new markets. In sum, sophistication is on the agenda more than ever. By sophistication and depth of debate, one should also understand the suitable academic environment, proper financing of projects, and increasing international cooperation. The Science Academy of Turkey has been established precisely carry out such an endeavor. As Bilgi, we remain deeply committed in interdisciplinary and international cooperation within the imperative framework of academic freedom. In that sense, it is our pleasure and privilege to host the Science Academy here in our premises. Let me again welcoming you all and hope all the success to the conference. Thank you for all the participants for being here. Thank you again. Thanks.
Thank you, Professor Yazgan, and of course İstanbul Bilgi University for hosting our academy on this occasion. We have received messages from the Minister of Industry and Technology, Mustafa Varank, and from the opposition party leader, Kemal Kılıçdaroğlu. I thank them also for their interest. I would also like to thank our Science Academy member, Professor Ayşe Buğra. It was her idea and her financial support that enabled our academy to start this series of yearly lectures by international guests, of which today we are holding the third. And we are very fortunate to have with us Professor Günter Stock. He is someone who is a real expert on today's subject. If you look at his biography, he has started being trained as a medical doctor, but he soon decided to actually move into scientific research. He spent the first part of his career in academia, doing research, and then he was called by industry, by Schering company, to set up from scratch a new research lab for this pharmaceutical company that was based on the new molecular biology. And he chaired this for quite some years and brought it, so he was doing both research and he was administering research in industry. And after that he has been active as president, first of the Berlin-Brandenburg Academy and then the German League of Academies, and finally he was a particularly proactive and successful leader of the European Academies Federation, ALLEA. He did many good things in ALLEA, so we got to know him when our Science Academy started the process of membership and eventually was fully admitted member of ALLEA. And during the same time, under Professor Stock's leadership, the academies and learned societies of Europe made a big political venture. They got the European Commission and European Parliament to agree for a formal mechanism to provide support by experts from research, from academia, from the very old venerable academies of Europe, to accept consultancy, to accept reports on science and technology on the new developments facing us. And this science advice mechanism has been now in operation for 2 years and a bit more, already publishing very important results on trying to enlighten policy on issues of modern science and technology. So today, Professor Stock will talk to us, and his title will be From Invention to Innovation, a short history of the biotech industry. Now, innovation and basic science applications to technology and basic research have, of course, always been connected, even when they were not even called science and technology in the pre-modern times. There was a symbiotic relation. But with modern times, on the science side, particularly with Galileo, with the precise introduction of the scientific method, research became something well-defined. And then it becomes clear what the dual relation between innovations, new technology, and basic research was. And this was followed by the gradual development and emergence of social institutions for both of these ventures. In particular, in the 19th century, started the von Humboldt definition of universities, research establishments, universities, followed soon after by institutions dedicated outside the university or linked with universities dedicated to research. And then these institutions were supported both by governments and also by private companies. This is relatively recent, this level of organization. And new institutions, new modes of organizing research and innovation and supporting it started to emerge. And in the 20th century, we now faced really big science. It became, in some cases, at the level of international collaborations. Great sums, great numbers of people were dedicated in these organizations, both for applications, innovations, and for basic scientific research. And at the same time, of course, this 20th century was the age of development of new areas of science, quantum physics, molecular biology, and computers and computational powers. So science itself started to be able to really go into deeper problems, and problems of emergence, problems of new complex systems, and to be actually able to discuss and quantify interfaces and emergence and complexity. And this has gone on to new areas, new avenues, both in science and technology, and also in the social sciences, because it became possible, at least more possible than earlier, to observe and to discuss emergence of social and economic structures by the new methods of science. And this, of course, had impact on society at large, on politics, and on the economic development of the world. Now, of course, innovative new technology is playing a very important role, not always a beneficial role, as we see in the environmental problems, but it's again the methods of scientific research and innovative technology that can help us solve these newly generated problems. So the whole issue of the emergence of new science, new innovation, and the relation between them is accelerating, has become very clearly on the forefront, very important. And it has also introduced a lot of jargon, sometimes empty words, just appeals to the public, you know, we are doing very innovative things and so on. And the important aspect there is never to forget that every innovation is related to basic research in the background. And it's something rather specific and concrete, though it can be complex, that has to be administered. And so I return now to Professor Stock's title. He will give us a specific and concrete example in the case of the evolution of the biotech industry and its relations with research. Professor Stock, please.
Good afternoon. It's a real pleasure to be here and to be welcomed so nicely. Thank you very much. A couple of years ago, the former president of Max Planck Society in Germany presented an analysis of patents in the US-American pharmaceutical industry, and the most remarkable result was that more than 70% of all publications which were the basis of the pharmaceutical inventions and product innovations were produced in academic laboratories, were produced by what we call basic research. In our general understanding, basic research is this type of research which is curiosity-driven, not primarily application-oriented, but directed towards a better and deeper understanding of the mechanisms underlying basic functions. Being myself a medic, I should add that to my understanding, this definition is also correct in the research we are doing in medicine and biomedicine. However, most of us hope at the same time that our research somehow will contribute to a better understanding of certain diseases. But in most cases, our research is not primarily product-oriented, it's rather oriented towards understanding mechanisms of physiology, especially pathophysiology, and identifying possible targets where we can then work on to find new regimens for treatment. And with this broad definition, of course, most of the research, also in other fields, is somehow related to improve the conditio humana. This means that basic research is primarily a mechanism which is process and method-oriented rather than product-oriented. And nevertheless, the transition from basic research into what we call applied research can be very and extremely short. Applied research has clear goals. In most cases, we aim to come up with new and better solutions, with better products, with better processes. And the more we learn, we can bridge the gap between basic and applied research, in many cases better and even faster. What we also learned is that in many cases, problems and questions arise from applied research which deserve a new approach in basic research. Therefore, in our today's life, we no longer describe basic and applied research as sequential events, but rather as an interactive, interwoven process where basic research can rapidly turn into applied research and vice versa. This is also the reason why in many companies, especially in the pharmaceutical industry, the paradigm of the last century, where basic research is being performed in academic laboratories and applied research in industrial laboratories, is no longer valid. Nowadays, a lot of academic researchers in the medical field are translating their results from basic research into applied research, which is product-oriented. While many industries, many companies spend a lot of money already in basic research in order to be able to come to innovation products and solutions early on. And related to this paradigm change is, of course, the question who owns the patents, which of course is of paramount importance in the pharmaceutical and in the other industry. In the pharmaceutical industry, the stacking of patent costs can be rather extensive if you have to take the licenses for targets and for many or at least some specific methods. And therefore, it can be quite interesting to companies to produce patents at the level of genes, proteins, and others, areas which used to be the domain of what we called basic research before. Hence, more and more public-private partnerships exist between academia, and the industry. But it also explains Why the industry wants to have access to the patents early and academicians want to see their research results being translated rapidly to new products, eventually also in money. This desire can be fulfilled by public-private partnership, or, as an alternative, by creating startup companies out of academia, an endeavor which not only needs good science, but especially excellent entrepreneurship, which is not the domain of today's university education. In fact, in recent years, we have seen both a fantastic increase in public-private partnership contracts worldwide, and in Germany as well, probably in your country also, but at the same time, we also saw an enormous amount of startup activities, creation of new companies. Most of them in recent years in medicine, today more and more in information technology. Of course, because of the high risk associated with drug research and development, many of the startups were not successful or only successful to a certain extent. But some of them made it and became very successful companies. This development is the reason why Big Pharma has professionalized their research activities for new ideas, for inventions, to translate them into innovations. As we recall, one of the first startups in biotech was Cetus, founded already in 1971, followed by Genentech, 1976, Biogen, 78, Amgen, 1980. Many others followed. We know from history that in the field of information technology in general and many other fields, the same picture can today be drawn. Again, being a medic, I would rather like to concentrate now on the pharmaceutical industry, which I know best and which I feel still gives a perfect example to trace back the emergence of what we now can call biotech industry. Even better is the basis for what we now call molecular medicine, and going beyond, calling it now personalized medicine today. The following I will try to show how this development started and how it transformed not only understanding of basic mechanisms in biology, but at the same time paved a fantastic avenue into new diagnostic and treatment options. It was Eugene Russell who published in Science in January 2003 a paper where he described how biotechnology became reality and started to transform medical research. And I will try to highlight important events which can give us hints how important inventions eventually were transformed into innovations. Eugene Russell writes that modern biotechnology started during a scientific congress in Honolulu in the year 1972. According to his narrative, Stanley Cohen, medical researcher working at Stanford, and the biochemist Herbert Boyer from the University of California, San Francisco, met and discussed Cohen's experiments in which he managed to introduce plasmid DNA in Escherichia coli. Boyer, on the other hand, had shown that double-stranded helix of the DNA could be separated into single strands with an identical terminal region. Over dinner at Waikiki Beach, accidentally this shows that scientists never stop working, even when they enjoy good life in Hawaii. During this dinner, they decided to combine these results in a series of experiments, and in fact, they managed to clone DNA and to produce recombinant DNA, the beginning of modern biotechnology. Eugene Russell considered this fact, in fact, as this beginning of modern biotechnology. And no doubt, this is correct. However, it does not fully honor the research which has led to this revolutionary result. There were a lot of forerunners. And this is why I'm trying to show why what Russell described as an initial step of the birth of biotechnology, I would rather like to call an intermediate step. And I will go back in history. And I will start this history with the German physiologist and anatomist Johannes Müller, who in the 19th century already realized and postulated that all biological activities of human beings follow the same principles in physics, chemistry, and this is true in all animals at the same time. Without this basic finding, nothing else would have been possible to develop. And of course, one should not discuss the development without Gregor Mendel, a monk living in today's Slovakia, who described the basic laws, or better, the principle of heredity for the first time. A big step forward brings me to Thomas Hunt Morgan, a man who is rightly called the father of genomic research. He could show that Mendel's laws, originally described for plants, is true also in fruit flies, and thereby proving what Mendel postulated for plants is true for animals as well. He gave evidence that genes are situated on chromosomes and that there is a clear order for the genes on the chromosomes. And finally, it was the description of the double helix by Watson and Crick who revealed the structure of the DNA and who also then described functions of RNA. Can I get the first slide now? Do I have to do it myself?
Yes, exactly.
It is hard to work yourself.
Yes,
Yes.
I can also press it.
One of the principles, of course, is you know to have the structure in order to work on that structure. So this was a very elementary finding of these two gentlemen. My second slide is an, now I have to put on my glasses. With the second slide, I wanted to show something which is now unfortunately missing. With the second slide, I wanted to show how stepwise the biotechnology industry evolved. First in the Bay Area, in San Francisco, and later on around the world. Now, the slide should show that with Watson and Crick, a breakthrough was made in this field. Foundation of many new innovative companies created quite some interest in circles of people, and this is now important, who had money and were prepared to risk this money by investing in these new startup companies. The idea of venture capital was applied in the area of biotechnology. In fact, enormous amounts of venture capital was given to these early biotech companies. Actually, later, but only later, also public money came in large quantities into this field in the United States. Hence, one should say that it is fair that venture capital had a major impact on the development of modern biotechnology and then followed by public money in the same way. Of course, this development was primarily taking place in the United States, and I should add quite some time. And finally, other countries followed to a certain degree. For example, in Germany, public money became available before venture capital came in this new research field. But in all fairness, we are still not good enough in providing venture capital to new technology areas, which is probably due to the rather high risk aversion which we have in my country. I wish that in your country this situation is much better than in mine, and we are learning, unfortunately, only slowly. It was not too long until human insulin could be produced in the year 1978, a breakthrough and at the same time a proof of concept. Let me pause for a second and make the point that this historic sketch, which is by far not complete and by far does not give justice to the many, many researchers who contributed as well, show that basic research in very different disciplines and labs led into what later became known as gene research, biotechnological research, and today medical biotechnology industry. Actually, I don't know when for the first time people started to think that this development could revolutionize our medical knowledge and our pharmaceutical industry. In fact, all the health business, agro, animal health business as well, are now part of this huge movement. Not to speak of the white biotechnology, the field of producing new basic chemicals primarily used in industry for further processing procedures. It's probably fair saying that a few pioneers in the 70s and venture capitalists probably at this time had a hunch that something really, really great and big would emerge. Let us turn now again to the pharmaceutical industry and to show what kind of history we had in those days. If we look back in the 50s, it was a very complicated field. Chemists came up with new chemical entities, and the poor pharmacologists, the poor clinicians, had hardly anything to prove in a scientific way. It was trial and error. In the 60s, fortunately, receptors came up, enzymes came up where we could work on, and you see still there, we had a number of 500 for targets where you could work on in terms of biological intervention. It was not many, and most of them were published in the public domain. In the 80s, finally, it was the start of molecular medicine research, and finally we got proteins as drug substances. I mentioned insulin. And then it really went on in the 90s that we had genomics, proteomics, combinatorial, all the X's which you can think of started in the 90s, and all of a sudden an explosion of new targets for interesting new drug finding. So this was the real beginning, and it totally changed the way how we do drug finding today. It was exactly these days when in the pharmaceutical industry everybody realized that a new dimension of research was at the horizon and was feasible at the same time. It was exactly in those years when I left academia, University of Heidelberg, and joined a company in Germany. And we decided early on that it could be an advantage to look into these developments of the new fields. We created a couple of institutes and acquired quite some companies. And we had to find out that the speed with which we acted was by far not fast enough. We created a lot of more research institutions, but at the same time, we created a network, an international network of public-private, public-public partnerships. All of a sudden, academia and startup companies, other companies came into play, and you see that each step of the drug finding process needed cooperation with completely different fields of research, most of them being companies. So this public-private network is also something which is part of the development in the 90s, which is now classical procedure in all the companies. This is preclinical development only, but it is true for the rest of the development as well. And in fact, 1993, we were successful by bringing to the market a drug to treat multiple sclerosis, the first ever. And this drug in multiple sclerosis was interesting because it opened up the field for immunology treatment, which we did not have before. The interesting point was all of a sudden in this field, publications went up and many researchers turned into this field with the result that now immunology is one of the most active and vivid fields we can think of in pharmaceutical industry. And it is also a fantastic field for research and successful research. Of course, many other companies did similar things. Again, first in the United States, later on also in Europe. Swiss companies were very successful at the same time, and all followed the same pattern. Acquisition of biotechnology startups, preferably, of course, those who had products in development derived from biotechnology. And we as middle-sized pharmaceutical company were probably forced more than others to enter into many, many public-private partnerships in order to access all the modern technologies which were needed to successfully develop innovative new drugs. The consequences for our research were clear. In the beginning, classical methods of drug finding were slowly but subsequently more and more rapidly replaced by in vitro technologies in pharmacology, biochemistry, and the metabolics and toxicological studies. The era of molecular medicine had transformed our mode of thinking within only a few years. Our way of thinking, our way of doing experiments, our way of finding new drugs, all of a sudden, trial and error to a large extent were replaced by hypothesis-driven scientific approaches. These days were truly interesting. Not only were a lot of new companies acquired, but at the same time, pharmaceutical industry also created new startup companies in which scientists who wanted to be independent continued their research work in their own company. The fact that all of a sudden so many new targets were available for drug finding, it was impossible for the companies, especially also, of course, for our companies, to address all those targets. We had to concentrate, everybody had to concentrate, we had to focus, and thereby some of the targets were given to individual researchers who then founded their own company based on drug finding with those targets, which we could and others could not pursue. A fantastic time and era for innovations, both in big pharma and in startup companies. So in these days, startup companies were brought up, but also were created completely new ones. What is the situation today? And here, again, let me look at Germany. And this is an example to show to what extent drug finding has resulted now in biotech products. You look at the year 2016 on the left side, all of the products in Germany, 75% are the classical drug finding, and you have 1/4 biopharmaceuticals from bioindustry. Within 1 year, there was an increase by 10%, which is now increasing there, and it continues to be there. In a few years, we will have 50% of all drugs being based on biotechnology products. So it's a very, very short period of time which has changed the pattern completely. It is mainly oncology and immunology, of course, and it's the rare diseases which benefit especially from this development. We have many more in the pipeline, and as I said, 50% is in the near future to be reached. Let me conclude. At least in the field of biomedicine, it is a long way from the first invention to breakthrough innovations. In the beginning, it is not always clear where the basic research will lead us. But ingenious research, ingenious combination of knowledge, which is there, it can lead to breakthroughs. Hence, it is obvious that basic research, curiosity-driven research, is the humus of all. Here, breakthroughs are made possible. Quantum leaps in knowledge, understanding and application of available knowledge is possible and reality. You cannot exactly plan and design inventions and not innovations. You need best efforts, good hypotheses, but you already have to be aware that the outcome of your experiment can be different from what you planned, from what you expected. And you have to be prepared to interpret the unexpected properly. And as stated before, you need endurance. This year's Nobel Prize, the two of them in medicine, are perfect examples. The first, the question why our almost perfect immune system does not recognize tumor cells. A long, strenuous way in research to understand this phenomenon, and now we have already new treatment options from this long-term research. The second example, in chemistry, to apply evolution principles to optimize proteins, long time a field in basic research where nobody believed in long time. So relevant questions about natural phenomena, carefully designed experiments, not to find products primarily, but rather to find an explanation for interesting phenomena, endurance and openness for the unexpected. All these are indispensable elements in basic research. So my first message is, research policies should be aware of this importance and should not ask too quickly and too early for applied research, often neglecting basic research. A trend which can be observed in quite a few countries nowadays. Without a broad basis in basic research, the ensuing applied research will soon die out as well. Second message, if we look at biotechnology, the success would not have been feasible without new materials, without new technologies, without new instruments, without new processes, in brief, without inter- and transdisciplinarity. Message 3, public-private partnership, cooperation across not only different fields, but also across different institutions and across different financial sources. Private and public money allows quantum leaps in the development of innovative products. Message 4, most important is personalities who are convinced about their work, people with courage and vision. And message 5, research institutions have to be autonomous in their decisions how to achieve their research goals, and they, in turn, must give this freedom to their individual researchers, who then will, based on their enduring curiosity, find evidence and create inventions that work to prove the concept and finally enable the translation of their findings in developing new processes, methods, insights, products. Hence, we need individuals who have an imagination to what end, to what kind of innovation the basic results can eventually lead. These individuals must have the entrepreneurial spirit, and/or they should look for partners who have exactly the ability to foresee the putative application of the invention. They need to network with synergistic partners, and in addition, they have to find money for the applied research needed to develop the idea into a product. In fact, we also need the appropriate surroundings, the appropriate infrastructure. We need autonomy, we need the infrastructure in physical terms, and we need money, public and private money. Public money is often granted on the basis of past performance. It is input-oriented. Private money is often interested in future gains. It is output, it is outcome-oriented. If both perspectives can be met by researchers, success is feasible. Finally, things work best if relevant industries can be made interested in the early ideas. They provide output orientation, but also professional advice on patents, concept proof, development skills, and marketing information, and skills as well as activities regarding market access and, in pharmaceutical especially also important, reimbursement issues. So new inventions nowadays, in addition to research in pharma companies, often also comes from non-industrial sources, but in many cases they need industrial partners in order to succeed. Highly competitive academic research, integrated in and cooperating with other disciplines in international networks, with a positive entrepreneurial surrounding in close connection with industrial enterprises, this might be the secret of successful bridging for inventions into relevant innovations. I would like to come to an end and say innovations have different facets. Some of them are breakthrough innovations. They change the way of doing business radically, as is the case for biotechnology in medical research, where we learned to diagnose and to treat diseases on a molecular level, and in some cases even at a truly personalized level. Some breakthrough innovations created completely new business fields, as is the case in the world of IT. But in addition, there are also innovations that have a clear benefit, but not as dramatic as the first type which I described, and they should not be overlooked and not be neglected. Our industry, the pharmaceutical industry, has many years been very successful and still is in slowly improving the efficacy of slightly modified treatments, while at the same time reducing unwanted side effects. And to a large extent, many of the innovations do have this character, which must not underestimate, and that which is true in many other fields, also outside medicine. And don't forget innovation in procedures. They could be technical, they could be process-oriented, which are, in the medical field, of great importance. Only think about the IT role we now have in medicine. The last words are directed towards our modern society, since this is an invitation of an academy and how they perceive innovations. There are societies where innovation is appreciated, is welcomed, mentally supported by the public. Therefore, research and the application of their results can flourish. Look at the United States and especially at Silicon Valley, today #1 in IT. The same area some years ago was the #1 area for biotechnology. Both of them now flourish, not only, but especially in this part of California. Societies which are more critical and more hesitant towards innovations, towards the application of new technologies, are honestly less successful. Therefore, these societies have to learn, and they have to learn faster than they did in the past, and they have to learn to adapt. I'm confident that this will work, but to that end, we, on the part of science, we had to adopt fair processes to judge risk and benefit of new technologies, and we have to share this, we have to teach this to the public. And currently, we have learned to entertain ongoing processes of risk-benefit analysis over longer periods of time than only the once-a-time risk-benefit analysis at the beginning of new processes of new technologies. And I'm sure that this type of approach will help also societies which are not that or able and willing to accept early risks. A couple of years ago, we in Germany were very critical towards new technologies, just to name the green technology, biotechnology. We still are. The consequence is clearly visible today. We are no longer players in that field, irrespective of the fact that many of the fears which existed when the technology came up had not become reality. But now, people are just averse against this new technology without underlying this with evidence or even facts. And this clearly shows that the social climate, how we look at new technologies, does have a deep impact on our ability to be at the forefront of innovations, or rather not. Ladies and gentlemen, coming again to the academies now, which I already introduced with the last paragraph. What can academies do in this world? And I believe they have a very special responsibility. First, they have to care, not only them, but especially they have to care for a scientific infrastructure which allows inventions and later on innovations. Second, they have to care for the quality of the scientists and the scientific institutions in the society together with the academicians in other fields. It is a joint responsibility, a joint effort. And number three, finally, due to the credibility of scientists, especially those in academies, which we have in our societies, in all societies, by the way, academies are well-suited places to do something that we call today public engagement. And this is to create opportunities, to create a place where scientists and the interested public come together and discuss scientific matters, which in most cases do have a social impact, where those issues are discussed at equal footing between scientists and the general public. Never in life before has the impact of science been so great for our daily life and to what we recall, what I said in the beginning, on the conditio humana. As impactful, as important as it is in our days. And innovations only improve our lives if they are meaningful for and to some extent expected, but definitely accepted by the people. Thank you very much.
Şimdi bir ara vereceğiz. We'll now have a break. And after the break, we'll have a panel which Professor Stock will also join. And at the very end, after the panel, we'll have some time for questions. Thank you. Coffee break.